There is a rule the solar system follows that no one ever told you about. Every planet orbits the Sun on roughly the same flat level. Mercury, Venus, Earth, Mars, Jupiter, all the way out to Neptune. They circle their star on a disk so thin that if you shrank the solar system down to the size of a dinner table, the entire region where the planets live would be no thicker than a sheet of paper. Astronomers call this disk the ecliptic plane. You could also call it a prison. Every spacecraft ever built has launched from Earth, and Earth, like every other planet, sits in that paper-thin disk. So every rocket that has ever left this planet was already moving sideways, carried along by Earth's own orbit around the Sun at roughly 30 kilometers per second. That is not a detail. That is the central problem. When you launch a mission to Mars, that inherited sideways speed works in your favor. You are already heading roughly in the right direction. A small push at the right moment nudges the spacecraft onto a path that intercepts Mars a few months later. Efficient, elegant, cheap, relatively speaking. But now imagine you want to go somewhere else entirely. Not sideways, not around. You want to go straight up, perpendicular to the disk, out through the top of the solar system toward what lies directly above the Sun. The inherited sideways speed is no longer your friend. Before your spacecraft can even begin climbing, it has to undo the 30 kilometers per second it was born with, cancel it out, spend it down to zero. Then, only after all of that inherited motion is neutralized, can it start building new velocity in the direction you actually want to go. Engineers measure the cost of spaceflight in something called delta V, the total change in velocity a spacecraft must produce using its own engines. Reaching Mars from Earth orbit demands roughly 4 kilometers per second of delta V. Getting a spacecraft out of the ecliptic plane entirely, up to a high angle above the Sun, demands something closer to 30. 7 times more demanding than going to Mars. Nearly 10 times more energy than reaching the outer solar system. Think about that for a moment. Pluto is roughly 5 billion kilometers from Earth. The distance above the Sun that a spacecraft would need to travel to take a real polar view is, in absolute terms, a tiny fraction of that. But in terms of energy cost, climbing out of the plane is one of the most expensive journeys in the entire solar system. Distance is almost irrelevant. Geometry is the obstacle. This is the flaw you never noticed. The thin disk in which all human spaceflight has taken place, for every mission, every destination, every decade of the space age. The Sun is the closest star to Earth. We have been studying it since before we had instruments, and with increasingly sensitive detectors for over a century. We have mapped its surface, measured its temperature gradient, tracked its sunspot cycles, sent spacecraft to fly within a few million kilometers of it. Our understanding of the Sun is deep, detailed, and hard-won. And yet there are 2 regions of that star we have barely seen. The poles of the Sun sit directly above and below its equator. That sounds obvious. What is less obvious is how invisible these regions are from the vantage point of every telescope and probe we have ever used. Because every instrument we have deployed has observed the Sun from within the same flat disk as the planets. From that angle, the poles are always seen edge-on, compressed into a thin line at the top and bottom of the solar disk. It is like trying to study the detailed terrain of a mountain by only looking at it from a low horizontal angle across a lake. You can tell the mountain is there. You cannot see much of what is on top. This is not a small problem. The polar regions of the Sun are where some of the most consequential solar physics happens. The solar wind is the constant stream of charged particles flowing outward from the Sun in all directions. It fills the entire solar system. It creates space weather. Strong bursts of solar wind can disrupt satellite communications, threaten astronaut safety, and in extreme cases, interfere with power grids on Earth. The solar wind comes in 2 varieties. The slow wind, turbulent and variable, blows from the equatorial regions. The fast wind, cleaner and more consistent, originates from large open magnetic structures at the poles called coronal holes. If you want to understand the full behavior of the solar wind and predict how it will affect the space environment of the inner solar system, the polar coronal holes are essential, and no one has ever observed them directly from above. The magnetic field of the Sun reverses its polarity on an approximately 11-year cycle. The north magnetic pole becomes the south, and then back again. This reversal is the heartbeat of the solar cycle and drives the pattern of sunspot activity, solar flares, and coronal mass ejections that define how active the sun is at any given time. The reversal begins at the poles and cascades toward the equator. The entire process is still not fully understood in its physical details, in part because we have never watched it happen from the right direction. The planets are not the outer edge of the solar system, not even close. Surrounding everything, expanding outward past the orbit of Neptune and far beyond, is a vast structure called the heliosphere. It is a bubble of solar wind influence, a region where the particle flow from the sun is dense enough to push back against the interstellar medium, the thin gas and dust that fills the space between star systems. Inside the heliosphere, the sun dominates. Outside, the galaxy does. The boundary of the heliosphere, the surface where solar wind pressure and interstellar pressure balance, is called the heliopause. The Voyager probes crossed it, Voyager 1 in 2012, Voyager 2 in 2018. They are the only human-made objects to have passed through it into interstellar space. But there is a fundamental thing about our heliosphere that we still do not know. We do not know what shape it is. For decades, the textbook answer was simple. The sun moves through the galaxy, and as it moves, it pushes the heliosphere forward in the direction of travel. The front is blunt and rounded, compressed by the incoming flow of interstellar particles. The back trails away into a long comet-like tail. This was the accepted picture. It appeared in diagrams. It was taught in classrooms. It seemed physically reasonable. Then in 2020, a research team at Boston University, led by astrophysicist Merav Ofer, published a new analysis. Their model, built on data from NASA missions, suggested the heliosphere is not comet-shaped at all. The revised picture looks more like a crescent or a flattened sphere with two jets extending from the sides, curling back but never forming a long streaming tail. The shape is fundamentally different. We do not have a definitive answer yet because we have never seen our own heliosphere from outside. The Voyager probes crossed the boundary, but they did so moving through the plane of the planets, nearly perpendicular to what would be the best viewing angle. Their crossing gave us detailed measurements at specific points. It did not give us a map. To actually see the shape of the heliosphere, you need a viewpoint well above or below the ecliptic plane, a spacecraft far enough out of the disk to look back at the entire structure from a useful angle, the way you might lean back from a dinner table to see that its surface is actually circular rather than just a strip of edge. From inside the disk, you will never get the whole picture. You need height. We live inside a bubble of unknown shape, inside a solar system whose poles we have barely seen, in a plane of orbit so gravitationally dominant that escaping it costs more energy than any interplanetary mission we have ever flown. So, how do you actually do it? The energy cost of escaping the ecliptic plane is not a problem you can solve simply by building a more powerful rocket. Even the most ambitious launch vehicles ever designed could not carry enough propellant to cancel 30 kilometers per second of inherited orbital velocity and then add enough velocity to reach a high polar inclination on their own. The numbers do not close, but there is a technique that might make the journey possible. It is counterintuitive. It requires doing the opposite of what you want before you can do what you want. The technique is called an Oberth maneuver. It was described mathematically by the German physicist Hermann Oberth nearly a century ago, and it works by exploiting a non-obvious truth about rocket engines. The energy a rocket engine delivers to a spacecraft depends not just on the amount of fuel burned, but on how fast the spacecraft is already moving when the fuel burns. A rocket burn at high velocity in a deep gravity well produces far more orbital energy than the same burn in the emptiness of space. The math is exact. The effect is dramatic. Here is how it would work for a polar mission. You do not point your spacecraft upward and thrust. Instead, you aim it directly at the sun. You let the spacecraft fall inward under solar gravity, accelerating as it goes, until it is skimming through the sun's inner corona at its closest approach. At that moment, at the point of maximum speed, possibly exceeding 100 kilometers per second, you fire the engines. The fuel that would have done almost nothing in the outer solar system now leverages the spacecraft's enormous velocity to radically reshape its orbit. It is the gravity of the sun acting as a slingshot, but without the need for a target planet. After the burn, the spacecraft does not fall back toward the sun. It shoots upward, climbing out of the ecliptic plane on a steep trajectory toward the polar regions that no instrument has ever properly seen. There is another approach, slower and quieter, but deeply elegant. Solar sails. A solar sail is an enormous sheet of reflective film, sometimes kilometers across, that uses the gentle pressure of sunlight itself as propulsion. Photons carry momentum. When they bounce off a reflective surface, they push it. The force is small but constant, and over months and years it accumulates into meaningful velocity changes. A spacecraft equipped with a large enough sail could slowly spiral inward toward the sun, using increasingly intense sunlight to push harder and harder, gradually tilting its orbital plane as it goes. The most ambitious proposals combine both ideas. A sail-equipped probe spirals in close to the sun over a period of years, using solar pressure to push its orbit to a steep inward trajectory. Then, at perihelion, the closest point of approach, the spacecraft fires chemical engines to execute the Oberth burn. The two techniques amplify each other. The sail gets the spacecraft into position for the most efficient possible burn. The Oberth maneuver uses that position to produce more velocity change than either method could achieve alone. This is where serious mission proposals now stand. The combination of patience and explosive precision. Years of quiet spiraling, then one moment of maximum violence at the closest possible point to the sun, then a long climb outward into territory no spacecraft has traversed. Suppose it works. Suppose a spacecraft executes the maneuver correctly and begins climbing out of the ecliptic plane toward the solar poles. What does it actually encounter? The first change is in the environment itself. The plane of the planets is not clean space. Billions of years of collisions between asteroids, breakups of comets, and slow erosion of planetary bodies have filled the ecliptic disk with dust. This dust scatters sunlight. You can see it from Earth with your own eyes on a clear, moonless night. Look for the zodiacal light, a faint diffuse cone of illumination extending along the path of the planets just after sunset or before dawn. That glow is the dust disk of the inner solar system, lit from inside. A spacecraft climbing above the ecliptic would rise out of this dust within months. The sky above the disk is dramatically cleaner. The background light is reduced. Faint signals that would be buried in scattered noise from within the disk become detectable. Astronomers have long noted that a telescope operating from above the ecliptic plane would have a fundamentally superior view of the universe, particularly for detecting the faint light of distant star systems and potentially for identifying the weak biosignatures that might indicate life elsewhere. Then there is the solar environment itself. At the poles, the slow, turbulent solar wind that bathes the planets gives way to the fast polar wind streaming from the coronal holes. A spacecraft there would experience a structurally different region of space, one that Solar Orbiter has only recently begun to characterize from its still limited inclination. Instruments close enough to the poles could directly measure the processes that drive the solar cycle and generate the space weather that affects the entire inner solar system. And then there is the view itself. From high enough above the ecliptic plane, the solar system would resolve for the first time into its actual shape. The planets would appear spread across a disk, a flat ring of worlds with the sun at its center. The dust would trace the plane in a gentle haze. The heliosphere would be visible all around, its true geometry apparent from outside at last. We have pointed our telescopes at distant galaxies and resolved their spiral arms. We have photographed Neptune from billions of kilometers away and counted its moons. We have taken images of a black hole's shadow at the center of a galaxy 55 million light-years distant. We have done extraordinary things with light and lenses and radio waves. We have never taken a photograph of our own solar system from outside its plane. Not one. Every image ever captured of this neighborhood has been taken from within it. by instruments living in the same thin disk as the planets, looking outward or inward, but never genuinely upward. The view that would show us our home the way it actually is, a flat disk of worlds inside a bubble of solar wind embedded in the galaxy, is still a view no camera has ever recorded. That image does not exist yet. Somewhere in the future, maybe with a solar sail that spends years spiraling toward perihelion, maybe with an obeth burn that happens in a single violent second as the spacecraft grazes the corona, the first photograph looking down at the solar system from outside its plane will be taken. Until it is, we are living inside a place whose shape we can only theorize about, orbiting a star whose poles we have only just begun to see, on a flat track of worlds that physics has, so far, made almost impossible to leave in the perpendicular direction. And if you had to choose, would you send a spacecraft on the patient, years-long solar sail approach, or would you stake everything on the obeth dive, the fast and violent path through the corona? Let us know below. If you love exploring the universe, I'm sharing a video about what Voyager found at the edge of the solar system. Like, subscribe, and share.